conversations with J. Krishnamurti and so on. So that's a very long I pursued. It's been there, some thread has been there, and but then they were all like parallels, but that didn't give me strong grounding on what exactly that they are. They come more from the philosophical side, and so on. So basically, we take quantum entanglement and compare it with the basically the collapse of space and time and so on. They are there, but that didn't satisfy me. So, but when I encountered, there is a literature called Samkhya Karika, and that is a mind-boggling physics actually. That was really good, and and then I ventured into Aryabhatiya. So Aryabhatiya is proper mathematics. There is no sugar coating or. Are you able to see my screen?
Yeah, now we can see. Yeah. You may want to go to presentation mode, Srini.
When I share the PPT.
Yeah.
Right, so this was very inspiring because it's a proper mathematics and done in around 450 AD in the kingdom of Magadha, and this story was fabulous. So just started reading it and also ended up teaching. So and then there is another book called Leelavati, and that's also another fabulous work. And then I found that it's not just we have heard most of us would have heard about Aryabhata and Bhaskara and so on as the Indian mathematicians. But what we have not heard about is that itself is a big phenomenal lineage, and that comes all the way from the Vedic age. And the lot of work has been done, and particularly on the Kerala astronomers have done phenomenal work on the differential equations and power series and so on. Madhava and Panikkar. Lot of work has been done, and I feel that as people of Indian origin, at least the least we can do is to at least read them and try to see what has been done. And it's very inspiring actually when we read that, and particularly when you look at the time frame in which it was done, it's actually a hair raising. It's a fantastic experience. So what I have done today is it's Aryabhatiya is basically several chapters are there, but I try to collect a few slokas which are simple but yet very powerful, and at least that will give a flavor of if you the flavor of what is there inside, and hopefully that will trigger a lot of interest in further reading. So that is the motivation, and I try to combine a mixture of slokas, primarily around starting with the decimal place system. Then we will cover, Varga Koti Nyaya, commonly known as Pythagoras theorem, but that is very much there in Aryabhatiya. And then that is a very contentious sloka, because it's not supposed to be there, right? So, but it's extensively used by Aryabhata in all the calculations. And then we will cover the calculation of pi, and it's not called as pi in Aryabhata. He simply refers to as a circumference to diameter ratio, and how cleverly he handles that. That was one nice loka. And then we will cover a little bit of the Kshetra Ganitam, basically the area of triangle, area of circle, and so on. And then we will also cover one system of equations, how he solves a system of equations. And that's a little bit of I would say, the birth of linear algebra. And then we will try to touch upon, if time permits, we'll touch upon the Arsine table. The entire Arsine table is there in Aryabhatiya. Basically, he has basically derived the sine, cos, cosine, cosine, etc. The origin of trigonometry is very much there in Aryabhatiya because it does spherical trigonometry in 3 dimensions, without which no astronomy is possible, right? So in his some of his chapters, he goes very deep into that, and he has not simply believed in this Ragu Ketu, but he actually does the calculations of shadows on the planets, and basically the whole idea of grahanam, etc., is very mathematical in Aryabhatiya. We actually does the shadow calculations and the eclipse calculation. That is how even today we have our comes, basically predicting the cycles very accurately, and maybe that some work has to be done to correct some of the present cycles and so on. But it is very mathematical, and it doesn't combine any philosophy or religious. So normally in Indic text, we basically, like we deal with some fantastic philosophical explorations, but here it is a pure mathematical exploration. And yeah, so having said that, I'll just try to. So these are the things which I will try to cover today, and hopefully we have some time for Q&A. Okay, and I will start with a Mangala sloka I have not given here. So So the Aryabhatiya starts with a Mangala Charanam. And so Brahma ka Shashi Buddha Bhrugu Ravi Kuja Guru Gona Bhaganana Namaskritya Aryabhataha Tuha Iha Nigadati Kusumapure Abhyatyitam Jnanam. So basically he says, having bowed to Brahma, Earth, Moon, Mercury, Venus, Sun, Mars, Jupiter, Saturn, and the asterisms, Aryabhatta sets forth here the knowledge cornered at Kusumapura. So basically, the Kusumapura is uh, reference of the
What? Mute you. Yeah. Oh, that's what I muted. Okay.
are you able to see
Take it.
the
Yeah, he can hear you.
uh, okay, and you're able to see the deck, right?
Yeah, but yeah, it's not in the presentation mode. It's in the, yeah,
Uh,
now it's good. Now it's good.
now it's good.
Okay.
Okay, okay. Yeah, so basically, okay, this is just a starter. It seems Aryabhatta I was an Asmaka who lived at Pataliputra, basically the modern Patna, today's Bihar, basically, in Magadha, and wrote his Aryabhatiya there. And this is also well noted in the and Magadha in ancient times was a great city. That is where the Nalanda University was, and the famous UNESCO site of the on.
We are getting a lot of echo from somebody. Please, if you are not talking, can you mute, please?
So here you see that there was a special provision for the study of astronomy in this university. And you won't believe there is a section in Aryabhatiya which talks about how to build an astronomical instrument, a telescope of sorts. And it's not that there were no instruments built those days, and there were sophisticated astronomical instruments which were built even during the Aryabhatiya period. Because if you look at the some of the data, like for example, distance between the Earth and Sun, etc., the accuracy is actually stunning. It's basically it will only start deviating from the fourth decimal place. So they had ways of measuring, and very accurate calculations were done. And so Aryabhatta one has been designated as Kulapa. Kulapati or head of the university. It's like a vice chancellor, and highest position of the university. And he served as the Kulapa of the Nalanda University, which was which is a flourishing state in the 5th and 6th centuries AD. And history shows that a lot of it was attacked three times, and I think the last attack it didn't survive. Basically, the manuscripts were burnt for 3 months or something, and so that's why some of the Aryabhatta's later works we did not get it, and so it's not clear what was there, what was not there, etc. So whatever we have, we are just going with that. Um, okay, so then the next slide, try to project it. Okay, so Aryabhatiya itself has four main chapters. So one is the Geetika Pada. So the Geetika Pada covers the basics of the alphabetic numerical systems and the units of time and their cosmic scale, the table of sign differences, the R sign table, the astronomical parameters, etc. And then the Ganita Pada is where what we refer to as the mathematics. This is where our familiarity comes in. We address like geometry, algebra, and squares and square root, cubes and cubes, and some of the Kutaka methods, basically solving the linear equations. All those things goes in,
Srinivasan, Srinivasan, we
yes,
are getting a lot of echo. Is there a second unit on?
yes,
If the second unit is on, we'll get a lot of disturbance. If you have iPhone, iPad, you can have only one unit.
one second. I I don't have any other.
I think you can probably go back. It's okay now.
I will continue now. Let's see whether, because I don't see any. Yeah. So yeah, we were talking about the Ganita Pada, and Kalakriya Pada is of very great importance because Kalakriya Pada is actually getting revived now. So Kalakriya Pada is where we talk about the divisions of time, and if you remember, basically we will all talk about the Brahma's, Brahma's day, and let me check if I have that simulator with me. Yeah. So this is a simulator which I prepared for the class. So basically, this is like the concentric cycles of time. So this is the outside circle, which is kalpa equal to 1008 yugas. This is the Brahma's, and then you have the basically the Pitruloka, which is actually 30x the Earth's frequency. So basically nowadays there is an architecture called here, and Anirban Bandyopadhyay and then Roger Penrose. They are all taking it very seriously, and they have built a lot of AGI stuff with that, basically using this architecture. And his notion of brain itself is, basically you go from one frequency domain and then internally, recursively into another clock, a clock within a clock within a. It's a nested clock architecture. That's how they interpret it. And so this concept is used in some of the latest theories of artificial intelligence. And yes, succeeded in creating some kind of a model where there is no data required for training. So that's the different person. But the point is that the Kalakriya Pada seems to have inspired people to do some scientific work. And Golapada is where it's called as a Bhugola sphere, and basically that's where Aryabhatiya models. There are equator, there are latitudes, longitudes, all those meridian calculations, all those things are being done in Golapada. So you'll find proper astronomical treatise. Okay, so basically these are the four major sections of Aryabhatiya, but we will most likely be dealing with Ganita Pada today. Okay, because the others are a little, I don't think we can cover in this time frame. So mostly we'll be dealing with some few simple slokas from Ganita Pada, but they kind of are a reasonable representation of the Aryabhata's work. Okay, so we'll start with the decimal place system. I'll try to. So if you look at this sloka, right? Um, so the sloka itself goes like this: Ekam dasha cha shatam cha sagasram ayuta niyute tata prayutam koti chaturbudam cha vrindam karvam nikarvam akshobhyaha. So what does this mean, right? So Ekam is 10 power 0, 1. That is very simple. Then you have dasha. Dasha equal to 10 power 1. Ekam dasha, so 1 and 10. Shatam. Shatam is 100. Okay. Then he goes to the Sahasram is basically 1000. Up to that, it's very clear. Right. Then Ayuta Niyute. So that is 10,000 and 100,000. 10 power 4 and 10 power 5. Okay. And then Tata Prayutam is million. 10 power 6. Then Koti Chaturbudham. 10 million and 100 million. 10 power 7 and 10 power 8. Brindam is billion. Then Karvam is 10 billion. Nikarvam is 100 billion. Akshobhyaha is trillion. So the basically it's just a 10 power 0 to 10 power 12 is defined. And what shocks me is what is the need for defining a trillion or 100 billion, etc. So mostly it comes from the need to define astronomical distances, because he has to calculate the distance between the Earth and Sun, Earth and Moon, etc. And to basically come up with astronomical numbers. Maybe he envisioned that these numbers are required. So this itself is a significant contribution given the time frame. Okay, so this is a beautiful shloka which talks about the basic derivative system and the powers of 10. And so after the next one, so here this is basically the anatomy of the triangle in the Aryabhata context. Okay, so if you take a simple right angle triangle, basically the base is called as bhuja. Base is called as bhuja, and upright perpendicular is always called as koti, and hypotenuse is called karna. So this is the terminology. And then there is one more terminology called abada. So abada is the section of the base. So the section is called as abada. And then the base goes by bhuja, bhumi, bhu, dhatri, mahi. So there are multiple synonyms associated with that. And then karna is basically always a hypotenuse. And then the triangle itself is called tribhujam, tribhuja kshetram. So that is what is called as there is a technical name for a triangle. It's nothing but a three-sided figure, and the term samadala koti is here is refers to a perpendicular bisector, but this is actually a contentious thing, because later I think Bhaskara doesn't agree with that, because the word samadala koti refers to vertical line which divides the base into two parts. Okay, and so since the scalene triangle, in scalene triangle this will not hold good. The term samadala koti is basically contested by in Bhaskara's Bhashya. It's a very beautiful shloka, but I'm not going to cover that. But that shows that they were very serious about the choice of words, and it has to adhere to Paninian grammar, and then the words has to be self-explanatory, and you cannot use arbitrary words and so on. So basically, if I say bhuja, it should basically intuitively I should know that it's a base, and if I say samadala koti, then basically the moment you say samadala koti, then you'll actually apply grammar to that. Then you will end up saying that okay, it's dividing into two equal parts, and then it's basically not internally consistent, and hence it will be rejected. So looks like Panini was very, very influential in those days, and Paninian grammar was given a lot of importance. Any exception to that has to be proven. So they have to basically build a case for that. Okay, and I'm just introducing this triangle terminology because we will encounter that shortly. And so yeah, the technical term for Pythagoras basically is Varga Koti Nyaya. So Varga Koti Nyaya is the Aryabhata's technical term, and this is a very simple sloka which actually talks about the relationship between Yaschaiva Bhujavargaha Koti Vargasya Karnavarga Saha. So basically Bhuja square. So Bhuja square plus Koti square. Vargaha is the act of multiplication. So Bhuja square plus Koti square equal to Karna square. So basically this is the This is a fundamental equation which is being used everywhere for the relationship between the base altitude and the hypotenuse of the triangle, very famously known as Pythagoras theorem. Okay, but Aryabhatiya has defined it in 450 AD. Okay, and then comes the this is another interesting sloka. This is basically defines the value of pi. So here it goes: Chatur adhikam shatamashta gunam dvashashtistata sagasranam ayuta dvaya vishkambasyasanno vrittaha parinaha. So Chatur adhikam shatam. So basically, you add 4 to 100. That's what it means. Chaturadikam shatam. You just add a 4 to 100. Then ashtagunam, basically multiply it by 8. And then dvashastistata sagasranam. So add 62,000. Okay. And then it says, this is the approximate circumference of a circle whose diameter is 20,000. Ayuta dvaya. What is great about the sloka? So basically he clearly defines. So I basically do this calculation: 104 into 8, add 4 to 100, 104, multiply it by 8 and add 62,000, I get 62,832. Okay, and then the diameter is 20,000. So he says this is the circumference of a circle whose diameter is 20,000. So diameter is 20,000. So now if I do the circumference to diameter ratio, the 62,832 by 20,000, I get the pi value. Okay, so this is the very indirect. Basically, it's called a circumference to diameter ratio. It's not called as pi in the literature, but this sloka very clearly and accurately defines the pi without actually. You can basically go on with the decimal places. Nobody is stopping you from doing that. It's just that this ratio is basically the value of pi. Okay, so we covered the decimal place system, and then we covered the Pythagoras equivalent, and then we covered the sloka, which actually does the calculation of pi. Okay, and then we will move on to the area of a circle, Vrittaksha Kshetraphalam. So the sloka for the area of a circle. So Samaparinahasyardam Vishkambar the Hatam Eva Vrittaphalam. So we'll just expand it a little bit here. So Vrittaksha Kshetraphalam. Vrittaksha Kshetraphalam is the area of a circle equal to Paridihi divided by 2 into Vishkambaha divided by 2. So basically Paridihi is the diameter. So it's 2r. 2r divided by 2, you get r. And Vishkambaha is the circumference. So here is 2 pi r by 2 is pi r. Pi r into r is pi r square. Okay, so, and then here I'll demonstrate this. Basically, I'll start with, the pi into Vishkambardham square. And then basically it is reduced to, basically you can express the pi as Paridihi divided by Vishkambaha into Vishkambardham square, and then you do the manipulation, and finally you find basically it's nothing but half the circumference into half the circumference into half the diameter. That gives the area of the circle. And then comes the area of a triangle. Tribhujasya Falashariram Samadala Koti Bhujarda Samvargaha. Basically, Tribhujasya Falashariram, area of a triangle. Samadala Koti Bhuja Arda Samvargaha. Basically, half the base into Samadala Koti is the height, gives the area of the triangle. So that's the simplest formula. But actually speaking, he does define the three types: Sama, Dvisama, and Vishama. Basically, the equilateral triangle, right-hand triangle, and scalene triangle. And the area of scalene triangle is derived separately. But for brevity, I am not going into that. just for the, just to keep it a little lighter. Okay, so that's a complete chapter on the Trivida Kshetraphalam. It's a full chapter in itself, and it's a 1 hour lecture actually. So basically, okay, in Sanskrit, basically we take the sloka like this: Tribhujasya phala shariram samadala koti bhujarga samvarkaha. So it's basically one straight, one single word, right? But actually speaking, what we do is we do the padachedam of the sloka, and that itself gives you a lot of clarity. Tribhujasya phala shariram Samadala Koti Bhuja Ardha Samvarkaha. So if you split it like this, then it's very simple, right? So then it's, you know that, okay, I have Samadala Koti and then I have Bhuja Ardha. So half of the Bhuja, half of the base, and then height Samvargaha. So there is a multiplier factor is also there. So that means that I have to multiply these two quantities. Multiply Samadala Koti with Bhuja Ardham, I'll get the Tribhujasya Phala Shariram. So basically the Padachedam gives a lot more clarity, and then you can actually do some more grammatical analysis. So Phala Shariram is Phalasya Shariram. Tribhujasya Tisra Bhujaha Yasya Tasya Tribhujasya Bhujayaha Ardham Bhujardham. So basically this is a Samasaha compound, and then Bhujayaha Ardham Bhujardhaha Samadala Koti Cha Bhujardham Cha Samadala Koti Bhujardham Samadala Koti Bhujardyoho Samvargaha. So basically this is a grammatical deduction of the statement, and so this is a very nice sloka. So Tribhujasya Kshetraphalam Swasya Lambasya Bhujardasya Cha Gunana Phalam Bhavati. So here, ya reka tribhujasya shirsha bhagat bhujaparyantam avalambaka rupena tishtati sa samadala koti bhavati. So here he is, this is Bhaskara Bhashyam, he is trying to define the basically the Samadala Koti as the one which joins the vertex. Shirsha bhagat means vertex of a triangle, and then he basically says avalambaka rupena. So basically it stands perpendicular, and then he joins the vertex to the base of the triangle, and he avoids the connotation that it divides the base into two parts. He divides it into two sections. So yesha samadala koti eva tribhujasya aunatyam bhavati. So this is basically more of a Bhaskara's Bhashyam on the Aryabhatiya sloka of the area of a triangle, and you find the rigor of the rigor is more on the linguistics and internal consistency, and then also they somewhere they also take exceptions. For example, there is a place where the meaning doesn't match what is the meaning inferred by, say, the grammarian like Panini. So he takes a different grammar in order to fit it mathematically. He says the mathematics is more important than linguistics, and hence there's a healthy tension between the linguistics and the mathematics. So that's very interesting. And Bhaskara's Bhashyam is very difficult to read, but if we read it, then it's a crown jewel actually. It's a crown jewel. So you can get into the thought process of that time, which is amazing, and very difficult to believe that so much of mathematical rigor was practiced in those days. So we generally assume that the beauty in Aryabhatiya is, except for the Mangalacharanam slokam, where he basically gives obeisance to the gods and also to the land in which he is born. Other than that, there is not a single iota of any religious thing coming to picture. There's no beliefs at all. So that there is a pure scientific temperament which is manifest, and that's a very striking feature of Aryabhata. So you will not find any suddenly you will not say, okay, so bring a religious principle or a philosophical principle and then twist it. No, it's just pure mathematics, and no such attempt is being made in that. So it's a very, very rigorous and work done with very high levels of integrity. So that's something to be appreciated, because in those times, just imagine the influence of, we don't know how the society was, but looking at Aryabhatiya, I feel like we have a very, twisted understanding of the Indian society itself. It's a pure scientific spirit manifest in the slokas. Okay, so that was my takeaway. And yeah, this is one of the beautiful sloka which we'll quickly cover. So rasayunam gajadanam pinditanam prakrtvena Jekena padena kridayam sarvadena tad bhavatyevam. So I will try to first go to the actual thing, and then maybe I'll cover the sloka. So basically here the sums of all combinations of the unknown quantities. So this is nothing but say an equation with n unknowns. The sums of all combinations of the unknown quantities except one, which are given separately, should be added together and divided by the number of unknown quantities less 1. So the quotient thus obtained is the total of all the unknown quantities. This total quantity severally diminished by the given sums given the various unknown quantities. So he is describing how to solve the equation. And so I'll put it here. So basically here you have a set of equations where you have x2 plus x3 plus xn. So the first term is missing in the first equation, and then here x2 is missing in the second equation, and xn is missing in the nth equation. So he is describing a system of equations like this, and then basically he is telling the procedure to solve it. So basically here what we do is basically rewrite the equations as x1, x2, xn minus x1, x2, x3 up to xn, and then basically you can simply do the n minus 1 into x1 plus xn equal to a1 up to an, and then you can basically write s equal to a1 up to n minus 1, and then find the individual values. So once you solve, the s minus a1 will give you x1, s minus a2 will give you s2, and so on. So this is just one simple Kutaka method, and there are several Kutakas in Aryabhatiya, and also there's a very famous pulverizer algorithm. I just wanted to just give a flavor that linear algebra foundations were actually laid. How to solve a system of equations was very much in vogue, and there is a quadratic, there is a cubic, and so on. There's a whole world out there actually, but I just wanted to introduce this small equation so that we know that equations were part of the part of the genre of the Aryabhatiya. And so this one is a little deviation in the sense that this deals with the kinematics actually. Okay, and so here basically this deals with kinematic. Basically, bhakte viloma vivare gatiyoga anuloma vivare do gatyantarena labdau davi yoga kala vati teishyav. So basically here there are two cases. One is two rigid bodies moving in towards each other. So here basically it describes Gati 1 plus Gati 2, the distance divided by d by v1 plus v2, and then the other equation is d by v1 minus v2, where the two objects are moving in the opposite direction. So we have started doing kinematics, and the more important thing is there is another this is another fantastic sloka which talks about the Newtonian inertial frames of reference. Basically, you imagine boat. Imagine a boat where one person is rowing forward, and then you have a stationary person who is sitting on a chair, right? So as the boat moves forward, it appears like the person is moving backwards, right? So that is normal relative motion, and that is what is kind of described here. So basically, anuloma gatihi, having forward motion, naustaha, one standing on a boat, pashyati, sees, achalam, the stationary object, vilomagam, going in the opposite direction. So basically, a person in the boat sees the stationary person as if he is moving in the opposite direction. Just as the beauty of it is comes in the second paragraph. The achalani, stationary fixed, bani, stars, luminous bodies, Tadvate, similarly, Sama Paschima Gani, going uniformly westward, Lankayam. Basically, okay, when he says Lankayam, it's not Sri Lanka, it is equator. Okay, so basically here he is basically applying this phenomenon on Earth where a person on a boat is moving forward and he is basically experiencing the, yeah, as if a stationary object is moving in the opposite direction. The same way he is saying that there are asterisms moving from west to east, and it appears as if the asterisms are moving from west to east for an observer on Earth, which is actually moving from east to west. So indirectly, he is saying that the Earth is rotating about itself. And the another important thing here is that he is applying the same law of motion, relative motion from an earthly phenomena to asterisms, right? So, which means that is basically implying scale invariance. So, scale invariance is actually a, like what is applicable for atom is also applicable for a planetary body in Newtonian mechanics. So, the same concept he is actually applying here, which is which to me was a shocker actually. Right. So basically, it's not about relative motion. Relative motion is simple. You can always call it out. But to confidently apply that to a planetary body is something which is something to, mind bending actually. And if you look at uh, basically, there are a lot of debates on the IISc channel on, okay, so has he done relativity? Has he done this and so on? So, but the answer is that if you actually apply Kalakriya, then the whole notion changes into frequency domain. And you don't need the same equations of Albert Einstein to describe the reality here. So they are completely different, and the basically that goes into the clock within a clock architecture. It's a completely different frequency domain model of time, and so space itself has no meaning, and time becomes recursive. So it's a completely different physics altogether, and we are trying to unravel this kind of physics. Anirban is actually rewriting the whole physics based on this, and so it's not that he is doing something philosophically. He's actually working on at the nano level and so on. So, but the devices are all modern, but he applies this principle and then he applies certain assumptions of physics is changing, and I'm still trying to understand his work, but it's a phenomenal work he has done. So something which I think with a little more scientific background, I think you might be able to understand more easily. Okay, so one last sloka, I will just try to, just to show you the computation of Arsine table geometrically. Okay, so here, basically, okay, the this is the method. Divide a quadrant of the circumference of a circle into as many parts as desired. Then from the right angle triangles and quadrilaterals, one can find as many arc sines of equal arcs as one likes for any given radius. So that is Aryabhata's guidance. And so basically you can have a circle and then divide it into equal 30-degree divisions, and then basically you write a chord, and this chord is basically equal to the radius. So this O, B, and L form the right angle triangle, and then they have 60-degree angles, and then based on just by applying the principles, you can basically come up with r sine theta, r sine 60, 30, and so on. So I was able to calculate up to all these eight uh, quantities: r sine 15, sine 30, 45, 60, 75, 90. So all of them, it's possible to compute with very simple calculations, right? So in fact, the R sine table for full calculations are there in Aryabhatiya, and you can go deep into that. So basically, that without trigonometry, there's no way you could have done what he did. So trigonometry and spherical trigonometry are very foundation of the work itself. And yeah, so this is what I wanted to cover. I just wanted to give some space for some discussion and questions and so on, so that
Srini, thanks
we
a lot
can
for sharing this one. This
make
is
use of.
really amazing, and always wonder how we lost this knowledge. That's always surprises me. I think it's now open for
Yeah.
questions, so people can unmute yourself, and if you have any questions, please ask the questions.
Yeah, I have a question for
Go ahead.
Srinivasan.
Yeah.
It's an excellent coverage. Like you said, there's a lot more to Aryabhatiya than what you could cover in this short period of time. And I really appreciate
Yes. Yes.
your expertise. One thing that Aryabhata was not aware of, and for that matter, all the Hindu astronomers in the period were not aware of, was the Greek concept of precession, Ayanamsha. So that came much later. So all their calculations were off because they were not aware of precession. What's your opinion on that?
Okay, because I have seen, okay, not in Aryabhatiya, but in Sankhya Karika, the precession is calculations are done actually. Sankhya Karika is much older physics, but there I have seen the intergalactic precessions are applied applied, and in Aryabhatiya, whether or not he was precession of the equinox is one of the chapters in Aryabhatiya, so I am a little surprised that. I will double check on that because the precision calculations are very much part of the Golapada, and I need to double check on that actually, because I strongly suspect that he had applied the precision. If not, definitely in Sankhya Garika I have come across the intergalactic precisions are very much part of that. But yeah, I will confirm that. That's a good question. I'll confirm that. I'm not sure about it right now.
Thank you. Shishdara, go ahead and ask your question.
Yeah, thank you. Yes, it was very nice overview. I I have a question. I mean, a couple of questions. One is you mentioned at the very end R sine. Is that the same as the what we know in trigonometry as sine function?
Yes, yes.
It is. Yeah. So that raises an interesting point, and that is, you know, we tend to think of many of these trigonometric functions in terms of what today we recognize as, I mean, I think unfortunately the name has stuck, and that is Taylor series and Maclaurin series and all that. So it was expressed as a series. Now I was wondering whether there's any evidence in Aryabhatiya about whether he thought of these functions as a series of terms, just like what we have today.
Okay, there is a separate series in Aryabhatiya, but had we connected to the sine, cosine, etc., is something which I need to investigate. But
Okay.
then derivation of our scientific. Okay, that is something which I need to investigate on that. But however, the Kerala astronomers have done full power series, differential equation power series. The entire
Right.
Madhava's
Yeah.
pi value itself is expressed as a power series. So yes, the power series itself has been done. Whether it was done by Aryabhatta is a question actually. But Aryabhatta does have a chapter on the series itself. It's
I
not
see.
that not aware of the series. But did he express the sine cosine as a series? That is something which I am not sure at this point. I will investigate.
So, I mean, as an extension of the concept of sine, did he also go into concepts like tangent and all that? I mean, it would have been a natural thing to do, but I don't know to what extent that extension of what we consider today as trigonometric functions, he dwelled further into. So.
Tangent, I have not seen that. Well, I think sine and probably cosine is
Fine,
probably
I see. Okay.
there.
Yeah. The
How
reason
he
I
dealt with. tangent is something which I need to go a little, do some research on that.
From what I've heard, I mean, I saw some videos on Madhwa's contributions to this series expansions, and the series that he focused on was sine, cosine, and I think um, tan inverse of pi by 4, and that's how he got he was one of the people who calculated the value of pi to an
Hmm.
even greater accuracy
Great,
than was, let's say,
great.
calculated by Aryabhatta. So
No, Aryabhatta actually, okay, Aryabhatta does not talk about pi at all. He talks about
mhm.
the circumference diameter and he leaves at
That's
that.
right.
So
Yeah,
basically, it
which
depends on,
uh,
you can go to any level of accuracy by, like the division where you want to stop. Right.
I see.
So
I see.
Aryabhatta is very clever in that front, actually. He doesn't
Uh,
limit it and he doesn't call it as a pi also. He just
no,
talks
no, that's
about,
true. Yeah.
because we are interpreting that as a pi, as a post facto, but he only talks about it as circumference to diameter ratio. That's all.
So when did the term pi come into existence? I mean, how did it become pi?
Okay. At least in Aryabhatiya, I don't see any explicit notions of pi.
Hmm.
That itself is a little bit of a historical research.
Okay.
Maybe at a later stage, maybe that was um, at least from the Aryabhatiya and the Bhaskara point of view, I don't see them as defined as a pi in itself.
I see.
But I would like to look at the Leelavati to have some answers. So
Okay.
Leelavati is a slightly later work, and there is also a Gupta school. There is also some competing schools, parallel schools of thought of mathematics, apart from Aryabhatta. So maybe we'll have to look at that angle.
Was the concept of the irrational numbers alive at the time of Aryabhatta, or is that? I mean, in some, maybe not as irrational as a word, but some concept that differentiated things that did not converge, like pi, versus things that converge, like one divided by four is a convergent number. So
I think so. There is a, yes, there is a rational and irrational. Basically, a Parikarmashtakam, a complete
mhm,
chapter is there, because when you are dealing with um, yeah, there is a Bhinna Parikar. This is called Bhinna Parikarmashtakam, 8 operations on fractions.
I see.
So that deals with Bhinna Gunanam, Bhinna division of fractions, squaring of fractions, cube root, square root. All those things are the 2 chapters are there in Leelavati. So
Mhm.
yes, I think they were dealing with those things.
Okay.
Just to just want to show this book. Basically, it's a 1,000-page work, and it was done by Mohan Acharya in Chennai. And so basically, because it's very difficult to deal with the original texts, the
Mhm.
Sanskrit, and the way in which it's in a very, it's like our with our tensor equations, right? So it's like that. So to decipher that Sanskrit is hard. So he has done the hard work of mining that and writing some books, which are also in Sanskrit, but at least it's approachable for ordinary mortals like me. So people who are not native Sanskrit scholars, people who are used to the reading the bhashyas, think they will be able to handle it. But it's not impossible, but it takes time, and we cannot rely on these tools like ChatGPT, etc., because they're bound to give you wrong answers. At least when coming to Sanskrit, we have to be very careful with which tools we use. So yeah, so if anybody is interested, you can also purchase these books and keep it as a reference. So all these questions, a very extensive coverage of the mathematics.
What is the title of that book, Srini?
This is basically Lilavati. There are two books up there. This is the textbook of Aryabhatiya. As you see, the pie is engraved right there. Okay. This is a book on Aryabhatiya, and this is a book on Lilavati. And there are a lot more books. I'll probably send that link. And if you are, I think, I'm not sure they ship to USA, but you can always, when you're traveling, you can, I can help you out, procure and then pass it on. So uh, I'll send you that link. That's a very useful book. And it also has English translation as well. So it's possible to follow these books as well.
Srinivasan, I have one more comment.
Yes.
Aryabhata's time corresponds to the Gupta Empire. And the Gupta Empire was really revolutionary in Indian history in the sense that they allowed the Greek thoughts to come into India. They got many of the
Okay.
Greek works translated, like Meena Rajas, and there are several astronomical texts which were translated from Greek to Sanskrit during the time. Is there
Okay.
any reference to that in Aryabhatiya, or does it claim that it is all purely Indian?
I don't think there is any reference to that in, at least I've not seen any reference to the translation from Greek to this one in Aryabhatiya.
Yeah, because
No, I'm
in
not.
Rahamihira, he clearly says in a shloka that the Greek philosophers should be admired like the Indian sages, as almost as rishis because of their knowledge. Uh,
Right.
I wonder if Aryabhata does the same thing, or he just ignores them.
I cannot comment that he's ignoring them because I don't know enough of history of that period. It's very contentious. Because I have heard about both ways. So basically, knowledge going from outside as well, right? So basically, there was a conference which happened in Arab world, and that is when the first time the decimal place system went and then replaced the numeric, the Roman numerals and so on. That's where the whole mathematical revolution started, and that is the uh, historical version I know of. But this is definitely a news to me that they actually derived a lot from Greeks, but I don't see any references in Aryabhatiya on the Greek literature, deriving it from the Greek literature.
Yeah, the concept of Lanka is very interesting that you mentioned. Some people
Yeah.
were even saying that there is a physical place, but as you said, it just represents the equator. It's in the middle
Yes.
of the Indian Ocean, and there is no point there. But because it is the equator, if you're theoretically standing at the equator and looking up, you'll see everything moving westward because the Earth is rotating at the equator, in the
Right.
opposite direction. And so that's a wonderful thing. But I wonder
No, but
again.
one thing to note is that time Ptolemy was actually basically Earth's rotation about itself was not known at that time, right? So it was at least 300, 400 years before Ptolemy, and so the heliocentrism has its roots in Vishnu Purana, and we have references of the Earth rotating about itself. And Aryabhatta, though not explicitly mentioned, but there is an implicit inference of the Earth's rotation about itself in these lokas. So
Yeah, there
that's
is a reference to celestial North Pole also in the Dhruva Nakshatra.
yes.
So Indians were aware of that. But the practical observation standing at the equator and looking at the sky, that is very interesting. Was there, like, did they send a ship there to see, really verify the facts, or
No,
because
they
the
had a
Greek.
scaled down model. It's actually very interesting. You look at Golapada, right? So basically, they had some concept of Bhugola sphere, so which is a
Mhm.
scaled down version of the Earth, just like how we have this rotating this one, right? We have this the sphere which we rotate, and the whole
Celestial
world map
sphere.
is. Yeah, celestial.
Oh,
They had something called as a Bhugola sphere, where they mapped all the. That is where the whole Lankayam comes, and then they have precise calculations of the longitudes and latitudes, and that's very interesting actually, how they did that. And then some of the see if the calculations were so precise. What actually strikes me is the precision, the distance between, for example, Earth and Sun, Earth and Moon, etc. I mean, the accuracy is stunning for me. Given that they did not have sophisticated astronomical instruments like today, but the deviation is like hardly, it's almost like 99% accurate compared to the modern astronomical distances. So you can actually look at it. There is a very good book by Aryabhatiya by Shukla Sharma. It's available in archives. It's a difficult read, but it is definitely a very good reference actually. So you can go into Golapada and look at all these data, and you'll be shocked to find some of them are really interesting how they did that. I don't expect that kind of accuracy from 450, however brilliant they were, right? So that's something.
And was Ujjaini the Greenwich center when at Aryabhata's time? Because that was this observatory. That was the standard that was used throughout India.
Yes.
So that was already there in place, or came
yes,
later?
Ujjaini is referred. Correct. You're correct.
So he makes a reference to Ujjaini at that time, or
yes,
because he's from Pataliputra. So those two are different places. But Guptas also, there was a Gupta king in Ujjaini. So there was an astronomical center in Ujjaini during the Gupta period. So I was wondering if they were making calculations from there.
No, Ujjain is referred in Aryabhatiya. Yes.
It is?
Yes.
Okay. Thank you.
Very good, insightful questions actually.
Can I ask one more question? Sorry.
Yeah, go ahead.
Yeah. So you mentioned in one of the slides about the art of solving equations, and so I mean obviously in as much as that concept had evolved, I was wondering whether there's any indication to say that there was some thinking about, but because if you are talking about variables, you could also be thinking about the changes in the variables, and that leads to an extension of that concept of equation to differential equations. And I was wondering whether there's any hint of that in Aryabhatiya. So
In Aryabhatiya, I don't see the there are quadratic equations and cubic equations, but the idea of differential equation, I think there is a work called Yukti Bhasha, basically a proper calculus that is by Kerala astronomers. It's a slightly later stage development, and that is where they have dealt with the differential equations, etc.
I see.
Not in Aryabhatiya. Aryabhatiya, I think he goes basically several different Kuttakas are there, and then one algorithm, pulverization algorithm is there, and so on. But I don't see the concept of differential equation emerging there.
Okay. Because
any other questions?
No, I just wanted to comment that if you think about it, the entire life system is a series of differential equations, from birth to death of not only human beings but the entire universal system itself.
Well, it depends on how they. But then there is a permutation. There is chapter on basically permutations. So in Lilavati, so permutations with known sum of these and so on. But I don't see this one actually.
I see. Okay.
The differential equations are not developed, but it was developed at a later stage. It is there in the literature. Yukti Bhasha, Tantra Sangraha, and so on, later texts actually deal with the calculus, the carrot astronomers basically.
Okay, if there are no more questions, Srini, thanks a lot for giving your knowledge, sharing your knowledge with us. It's very interesting. One way it is sad to learn that we have lost this scientific thinking, but at least now we are trying to dig it and try to get some of the information back, and hopefully we'll be able to develop and establish. With that, let's close today's section, and maybe some other time we can come and take one of those four aspects of Aryabhatiya and give a presentation in a little bit more detail. I'm
Yeah,
telling
sure.
you. Yeah, okay. Okay, thanks you guys. We will see you next month, third Saturday of next month. Until then, bye.
Bye.
Bye, CS.
Bye.
Bye, CS.
Bye, guys.
Bye. Bye, Ramesha. Yeah.